Hi everyone, today is fun maths. 2 plus 2 equals to 5. Oh, what's this again? Today we are talking about inertia. What is inertia? Good day everyone, today we'll be talking about simple harmonic motion. So simple harmonic motion is just a type of periodic motion. And what do you mean by periodic motion? From the word period, it means something that occurs at regular interval. For instance, when your heart beats at regular interval. It's beat, boo, boo, boo. It occurs at regular interval. So whatever happens at regular interval is what we mean by periodic motion. Now, a type of periodic motion is like simple harmonic motion. And simple harmonic motion is just a type of periodic motion in which the restoring force, and you must note that it must have a restoring force. The restoring force is directly proportional to the displacement from the main position. The restoring force, it must have a restoring position. For it to be a simple harmonic motion, it must have a restoring force. The restoring force is directly proportional to the displacement. That is what we mean by simple harmonic motion. And why is it called harmonic? Harmonic means something that follows sinusoidal motion, which means sine wave. Which means if I have a sine wave like this, it's a sinusoidal function. So simple harmonic motion can be represented in this format, in this sine wave. That's why it is sinusoidal. And because it's sinusoidal, we call it harmonic, because all harmonic is called sinusoidal function. So simple harmonic motion is a type of sinusoidal function, and it is a type of periodic motion which has a restoring force. And this restoring force is directly proportional to the displacement. Some can say that simple harmonic motion is a type of motion in which the acceleration is directly proportional to the displacement. From the main point. It's still the same thing. I will prove both for you now. Now let's talk about the types of simple harmonic motion. We have mass spring motion, or we call it mass spring system. We have simple pendulum. And we have molecular vibration. Now, I'll be taking them one after the other. The first one I'm talking about is this mass spring system. And don't forget to hit the like button if you are enjoying this video. Now let's talk about mass spring system. Mass spring system now is just a type of system in which you have a spring. Let's assume you have a spring like this and you attach a mass to it. If you should apply force in dragging this or in compressing it, if you drag it this direction, remember the spring will expand and it will gain some distance. Now, this is the main position when you just add the mass to it, when it is not moving. When you add, remember this is the main position. When you add force to it, that force that you apply to it, this is the force you apply to it. When you apply force to it, it's extended to this position. It's extended to this point. Now, mind you, from here, from this point to this point is what we call amplitude. So that is the maximum displacement. The maximum displacement is what we call the amplitude. Now, any position in between this amplitude is displacement. Like from here to here is displacement x. We can call it x1. From here to here, we can call it x2. We can call here to here x3. But once it's from here to this maximum point. Know that is the maximum point. That is the amplitude. So we just use A to denote it. Let's know that. And when we release it, there is a restoring force that wants it to come back to this equilibrium position. There is a restoring force. This restoring force is now equals to this force applied, which wants it to come back to this restoring with this equilibrium position. So since the restoring force will be acting like this, you can see the displacement is going the displacement is going this way, is going this direction. Let's assume it is positive x direction, but the restoring force is going against it. So the restoring force will be pointing towards, because this is the main point. So the restoring force wants it to come back here, so it is pointing backward. That is why they said the restoring force is directly proportional to negative x, because you can see the direction of the displacement and the restoring force are in opposite direction. That's why they put this negative value for x there. So we know that this force is the same thing as the force applied, because it's equal to the force applied. So we can just say that we are representing this as MA. I say MA is directly proportional to negative x, and we know that mass is always constant, so we can omit it since it is constant, and this proportionality involves constant, so it can join the constant that is inside this proportionality. So we can just say A is directly proportional to negative x. That's why they can define the term SHM as the force that is directly proportional to the displacement, or they say the acceleration is directly proportional to the displacement. Those are the two ways. So let me put it at this corner, that the force is directly proportional to the negative x, and the amplitude and acceleration rather is directly proportional to the negative x also. All right, now let's now talk about going back. Now we have understood what an amplitude is, and we have understood what a displacement is. And mind you, a displacement is always from this point, from the main point, from this main point to any position, and it cannot exceed the maximum displacement, which is the amplitude. The x value is from this point to any point. So mind you, know when it is being given and what to do when it is being given. Let's note that very well. Okay, now when you release this object, remember this object, I said there is a restoring force that is pulling it like this. Since there is a restoring force that is pulling it, this is the main position. To the main position here, there's a restoring force that is pulling it there. So what happens is that the object, once you release it, the object starts moving back. And when it starts moving back, it will later end up coming back, because it won't stay at this main position. It will go beyond this main position. So it will now compress the spring. But mind you, it will compress the spring. But mind you, the distance between this one and this one was equal to the distance between this one and this one in SHM. And mind you, SHM is an ideal system, because it is not real. Because in real life, if you release an object, it will not reach the maximum position again. It will be reducing, which we call damping. It will be reducing in amplitude. It will be reducing in amplitude till amplitude diminish, and it end up staying at the main position. That is what real system is. But for SHM, we assume that it is moving to and fro forever, like it doesn't reduce. So the amplitude it has here was because to the amplitude it has. But remember, this is the main position, so here will be negative amplitude, so it's moving in negative direction. So the acceleration will be the direction of the displacement will be like this, while the restoring force also will opposite, because the restoring force wanted to come here. So as it passes this main position, the restoring force will face back that you have passed where I want you to be, then come back like this. Then the restoring force will start pulling back, and it end up being here. That is how it continues going. It compresses, then it shoots back, it come back here, it come back here, it shoot back, it come back here, come back here. So that is why it is periodic, because it moves to and fro, to and fro, to and fro. That is for mass spring system. Now let's start deriving formulas on this. But before I start deriving formulas, let's take note of something. Okay, what I want you to take note of is that, remember, at this position, okay, let me start from the beginning. At this position, x, at this position, x is represented as displacement. Our x is equals to 0 because you have not displaced it at all. As you drag it to this position, since it reaches the maximum position here, our x become a, which is the maximum position. But just before you reach this maximum place, your x will attain some values less than this guy. Then when it reaches this mean position, your x become your amplitude. Your x become your amplitude. Now, for when it is now going back, when it reaches this place also, your x is equals to your a also, because at here, but it is just negative value of that value. It is negative a that your x is equals to at this position. Now, if you are not talking about the velocity, now remember when it is at the mean position, you drag it to this point. When you drag it to this point, just before you release it, it has not actually start moving. Since it has not started moving, your velocity is 0. Just before you release it, your velocity is 0, and as it decreases, as it moves like this, your velocity starts increasing. As it reaches this mean point, your velocity is maximum. At this mean point, your velocity is maximum. So at this mean point, velocity is max at that mean point. As it goes back, that velocity that is max starts reducing. As it reaches here, the velocity becomes 0 again, and then it starts moving back. For instance, let us assume as you drag it to this place, and as you leave it, the velocity starts increasing 1, 2, 3, 4, 5, 6, 7, 8. As it reaches this place, 10. And as it goes back, the velocity starts reducing 9, 8, 7, 6, 5, 4, 3, 2, 1. And as it reaches here, the velocity is 0. That's when it stops and starts moving in opposite direction, like moving backward like this, and it continues like that. So at this point, the velocity is maximum. At this point, the velocity is minimum. And mind you, we talk about the potential energy and the kinetic energy later in this video. Just stay tuned, and don't forget to hit the like button if you are enjoying this video. Now let's move into derivation of formulas. So okay, now let's start deriving formula. The first thing that we know is our f that is directly proportional to negative x, and you can see that this actually is a spring. Then it will be Hooke's law, and you remember that Hooke's law constant is f equals to negative kx. Exactly what this thing change to f equals to, because once this constant proportionality is turned to equals to, there must be a constant, and the constant is k, and this k is spring constant x. So this k is spring constant. They call this force constant also. This k can be either be force or spring constant. So what it tells you is how stiffness this spring is. Maybe it is very stiff, maybe it is not very stiff. If it is very stiff, it means we have high value of k, and if you have high value of k, it means that for it to be stretched, you have to apply high force for it to be stretched. So that is what this k is. Now don't forget that this f that we call restoring force is what I said that it is actually equals to the force we applied, but once we have removed the force we applied, this f of restoring force will become mass ma, which equals to negative kx. I just changed this because we remember from second law that f force equals to mass times acceleration. From Newton's second law of motion, we know that f equals to mass and acceleration, so we represented f as mass over acceleration. Now we are looking for a. So our a is equals to minus k over m. If I should divide both sides by m, x. If I divide both sides by m, I will have a equals to minus k over m x. So we can now rewrite a. A is the differential of velocity. So we say that with time. So it is the change in velocity with time, or we say it is change the second derivation of displacement with time. So the x square over the t square. Also, this change in value that we are writing, we can actually write it as, instead of writing x over t, for instance, if I have the x over the t, I can represent it as x dot, one dot on top. If it is second derivation, the x squared, the 2x over the t square, I can represent it as x dot dot. So instead of writing acceleration, acceleration equals to d square x over the t square, so I'm going to represent it as x dot dot instead of writing that. So I'm going to write it as x dot dot. So writing that, I will have x dot dot equals to negative k over n x. Now this, let's take note of this, and if I should bring this thing to the other side, so it will become x dot dot my plus k over n x equals to 0. So these two equations, let's take note of them, or let me just say these three equations, let's take note of them. Let's take note of them very well. Now, since we said that this simple harmonic motion is a sinusoidal motion, now let's take note of two things also. The first thing I want you to take note of is a sine function. Remember, a sine function starts from the origin, it goes like this. And remember, a cosine function, this is a sine function. For a cosine function, it starts from a point and it goes like that. So that this is a cosine function. Now note that for this guy, for this simple harmonic motion, for this mass spring motion, I give it a certain displacement before I release it, before it starts going to and fro. So it means that as I drag it to a certain amount, it doesn't start from origin, it starts from this certain amount. That's why we are using cosine for this. So we can use sine also for it if it is starting from the origin. But for this example, we are starting from a point, which means we are using cosine function for it. And so we can represent it as x equals to a cos omega t plus phase angle. Now note very well, this is the equation of simple harmonic motion. A is our amplitude. Omega is our angular frequency. Now mind you, we can call it angular velocity, but angular velocity is being used in circulatory motion. You take note of that. So t is time, and this is phase angle. We can call it phase shift also, or shift. We can call it phase angle, we can call it phase shift also. So that is it, and this is our displacement. Now let's take note of this value very well. Now if I should take this function now, let me put it on this side and let's start using them. For the equation now, we have x of t to be equals to a cos omega t plus angular phase angle. Now let me differentiate this guy with respect to t to get our velocity. Remember, our velocity is change in position over change in time, which is displacement over time. So we have to differentiate this function, since we are having if we want to get our velocity. So I can literally say that my velocity is equals to the x over the t, right, which I can also write as x dot. Are you getting it now? Now let's differentiate. Now differentiating cos, now remember this is a constant, so the constant remains the same. I will put the constant back as a. Now if I want to differentiate a function a plus b, if I want to differentiate this function now, I first differentiate this guy, which is a plus b. When I differentiate it, I will first differentiate the a plus b. If I differentiate that one I will now differentiate this cos, which will give me minus sine. Then I will write all this back. That's how you differentiate sine and cos or any metric functions that is in this format. So you first differentiate the inner part. So after differentiating the inner part, then you differentiate the main function, which is cos and the sine, and then you write what is inside it back. So let's use that logic for our function here. So our function here, I'm going to differentiate this with respect to t. And mind you, if I should differentiate omega t, I'm going to have omega. If I should differentiate phi, since phi does not have, this phase angle does not have time, that will be 0. That will be 0. So we will have, and differentiate cos, we have minus sine. Then I write everything back. So if I write everything, we have omega t plus changing angle, phase angle. Then I can just say that my x dot is equals to minus a omega sine omega t plus phase angle. Now we have obtained our velocity, but mind you, we want to compare it with this equation that we have here, and we have acceleration here, not velocity. So how can I do that? Now I'm going to differentiate. That should differentiate. I will have x dot dot, which is the second differential. Now I should differentiate this constant. I'm going to put it there back, minus aw. Differentiate sine, you have cos. Then differentiate the inner part. Differentiate omega t, you have omega. So if I should multiply this by omega, I will have omega square. Hope you understand. Then this inner part, I will write it back. What we did is that we have sine omega t plus phi. Differentiate this inner part first, and this one is with respect to t, this one is having t, then that will be omega, and differentiate sine, you have cos, and you write everything that is inside it back. That's what I did. And this omega, multiply the initial omega that was here, which was here, this become omega square and become this function back. So if you want to know more about differentiation, I will still do video on that. Just comment and let me know your choice. And let's continue. We can see that we have obtained our acceleration, but now we can see that a cos theta is equal to our x, which we can see here. So I can say, okay, I can separate this into minus omega square a cos omega t plus phase angle. But this one is our x, so I can write it as this equals to our solution equals to minus omega square x. We can see it now. So minus omega square x is now our acceleration. Now if I should transport this to the other side, that we have x minus this plus omega square x equals to 0. Then we have the same thing with this equation. We have the same thing with this equation. We can now compare. This is this, all right, plus xx, which means our omega square is literally k over m. And we can see, since our omega square is k over m, we should take note of that also. That is one of the formulas we are going to consider. So we can see that our omega, which is our angular frequency, is square root of k over m. And don't forget, our k is the spring constant, while our mass is m is the mass of that object. A is acceleration, and that is how it goes. So don't forget this part also. Now if you remember that our omega is equals to 2 pi f from our circular motion, you can see that our omega equals to 2 pi f, and f, don't forget our f is 1 over period, and t equals to 1 over f. Don't forget our f is frequency, our t is period. Now from the spring mass constant that we talked about that time, so we know we have something like this, and we have a spring, that is a mass that's been attached to it. Assuming we have our main points to be here, so this from here to here is our amplitude that we discussed, and it goes back to this position when it's compressed. Now let's if we have that now, for a complete oscillation, it moves from this position. If we start from this position, it will move to and fro for it to become one oscillation. That's one oscillation. It must move to and fro. But if we start from this midpoint, it will move to the left, go back to the right, and go back to the main position, and that makes it one oscillation also. Now from this thing now, we can see that in one oscillation, how many amplitudes do we have? Just think of it. In one oscillation, how many amplitudes do we have? It's move from here to here. This is one amplitude. Move from here to here, another amplitude. From here to here, another amplitude. From here to here, another amplitude. We have 4 amplitude, which means one oscillation is equivalent to 4 amplitude. Now take note of that very well. Now if we are not talking about the period rather, we are talking about the period now. Period is the time taken to complete one oscillation. The time taken to complete one oscillation. The time it takes to complete one oscillation is what we mean by period. It may take much time to complete one oscillation. It may take less time to complete one oscillation. That is why it is time it takes to complete one oscillation. This is number of oscillation. Let's note that number of oscillation. This is number of oscillation, and this is time taken. So the time taken to complete one oscillation is what we mean by period. Why frequency? Frequency is now number of oscillations it makes within 1 second. We can see that they are inversely proportional to each other like that. So number of oscillation it takes to a number of oscillation it's performed within 1 second. That is what we mean by frequency. Why period is the time taken to complete one oscillation. So that is that about that. Now if you remember that, we can now come back to this guy, omega equals to 2 pi f. So we can see that our omega is equals to 2 pi, that should represent f with 1 over t, and we have 2 pi over t. Remember that our omega is right here, square root of k over m. So I can say it is square root of k over m equals to 2 pi over t. If I flip, I will have square root of m over k. Remember we are looking for our period, so I will have t over 2 pi. I just change them, flip them. So it's the same thing. It's like saying you have a over b equals to c over d. You can flip them and say you have b over a equals to d over c. You can say that. You can flip them. And having this, if I should cross multiply, I will have my period to be equals to 2 pi square root of m over k. Don't let us forget this formula also. We will use it. Now from here now, you can go ahead and just find frequency. You can find the frequency, and you can see that frequency is nothing but 1 over t, which means I'm going to flip everything that is here, having 1 over 2 pi, and flip this one also to have k over m. So we can say that our f equals to 1 over 2 pi square root of k over m. That is for our frequency also. Let us now find formula for velocity, and then we find our energy, the potential energy, the total energy, the potential energy, and our kinetic energy. Those are the 4 things that remain that we are going to derive formula for now. And then we learn how to use all the formula listed at the right hand side. If you recall that our x is equals to a cos omega t plus angular frequency, then we can say that our velocity, which is our x bar, is equals to minus a omega sine omega t plus phase angle. That is what we defined earlier before. Now let's find velocity in terms of x. Remember, this is in terms of our angle, phase angle, and all those things. But let's find it in terms of x, like our acceleration as we did here. So let's find our velocity like that. Now remember that this is sine, but our x is in cos form. So how can we, what is the relation between sine and cos? Remember that sine square theta plus cos square theta equals to 1. Then if I want to find sine in terms of cos, I will say that sine square theta is equals to 1 minus cos square theta. I just drop this to the other side and the sign will change. Then take the square root of both sides. Then sine theta equals to square root of 1 minus cos square theta. Since we have this now, we can now represent this sine omega t plus theta in this format. Then we can say that sine omega t plus phase angle is equals to square root of 1 minus cos square omega t plus this. Now having this, now we can just represent inside our equation that okay, our velocity equals to negative a omega square root of 1 minus cos square omega t plus phase angle. But if you should look at our x, it's having amplitude, but this is not having amplitude. Let alone of replacing it. Then we can just multiply this amplitude inside. And don't forget that square root of a square is equals to a. Then I can rewrite a as square root of a square. I can rewrite this like that, which means if this a is going under square root, it will carry a square. So this is now going on inside, it must carry square. So I will say this is equals to negative omega square root of a square, because it will carry square root, and everything that is there 1 minus cos square omega t plus 5. All right, now since we have this, now we can multiply through by a. So I can say my x, which is our velocity rather, x dot is equals to a square minus a square cos square omega t plus this. Then I can just bring out this square out, so I can say x squared equal x dot equals to minus omega square root of a squared minus a cos omega t plus 5 all squared. It's the same thing. A squared is a squared, omega t squared and cos omega t is still squared. Then I can recall that our x equals to a cos omega t plus phase angle. Then we can just represent it and say our velocity equals to minus omega square root of a squared minus all this become x and is carrying square, x squared. And don't forget this is a formula for your velocity. So I'm going to put it here. Our velocity is equals to minus omega square root of a square minus x square. Now note that very well also. Now let's talk about the potential energy and the kinetic energy, likewise the total energy. If you recall from our spring concept, potential energy is the work done stored in this is the energy stored in this spring, which is our work done. And since the spring force is variable force, because when it reduces with distance, it changes. It's a variable force. We have variable force and we have constant force. But for spring constant, the variable force. Maybe in another video, I will explain what a variable force, the constant force, the conservative, and a non-conservative force is. Now, since it is a constant variable force, instead of having force times distance, normally for our work done, which is equals to our potential energy mgh for gravitational force, we can just say that it is the integral of force. The x. Since we are using x, let's use x as our distance, like displacement. So if you are integrating this now, that's our potential energy. But now here, this one does not have x. So how can we modify this to have x? Now recall that our F equals to negative kx. Since it is equals to this, I can actually represent my force as kx, the x. Since I can do that, the constant here, I can bring it out, having k outside, integral of x dx. And if you are integrating a x, you add 1 to the power. You know, x power is the power of x. The power of x is 1. The power of x is 1. So you add 1 to the power and you divide it by that thing. So you have x squared over 2. So that's what, if you integrate this, you have k into bracket x squared over 2. And then you can just say your potential energy is equals to half kx squared. You can see this is your potential energy formula. So that is potential energy equals to half kx squared. But for kinetic energy, we all know that kinetic energy is energy that is due with motion. So we know that it is half mv squared. And recall that your m from your m equals to k over omega square. From omega square equals to k over m. From this formula, omega equals to k over m. If you are looking for our m, we can just cross multiply and say our m equals to k over omega square. So we can just represent this inside this, and we say it is half kv square over omega square. We can just derive a lot under it. We can represent it in forms of velocity. Since we can see the change you can see velocity here, we can actually represent it like that. So let's go ahead and do it like that also. So we have our kinetic energy also. If we are changing this velocity into this guy, so I can just say half m. Our velocity is minus omega square root of a squared minus x squared, all squared. Then I can say that we have our kinetic energy to be equals to half minus squared is minus. So we have omega square we cancel square root for the second one. So we have a squared minus x squared. So this is another formula for kinetic energy, but the basic is actually half k e squared. So I'm going to have half mv squared rather. So I'm going to write half mv squared. So let's now find our potential energy. All right, for our total energy, we know that total energy is conserved. Then we can say our kinetic energy plus our potential energy is equals to our total energy. Then our total energy is now what? Our kinetic energy is actually half mv squared, as we said earlier, and our potential energy is half kx squared. Now, for velocity, I can change it to this, as we did earlier. I can change it to omega square. It is also equals to omega square a square minus x squared from our former derivation plus half kx squared. Now, this k also I want to change it because our omega equals to k, our omega square equals to k over m. Then our k will be equals to m omega square, because I want to see the correlation between the two equations. So we can now say we have half, opening the bracket, half m omega square a square minus half m omega square x squared plus half k is now m omega square. So I can say m omega square x squared. You can see that we have half m omega s squared minus half omega of m squared. These two can cancel out. Then we can say that our total energy is half m omega square a square. But don't forget that our m omega a square is k. So we can still see that it is half k a square. So that is the last formula we are going to be talking about in simple harmonic motion. With this, we can solve a lot of problems. Now, let's now analyze it on the mass spring system. Now, for our mass spring system, we know that we have something like this. So if I should say that this place is my main position, this will be the end point, while this is the highest point. Now, at this higher point, don't forget my x equals to a. At this middle point, which is the main point, our x equals to 0. And at this end point also, my x equals to negative a, which is equals to a also, is just the convention. Now, if we are talking about our velocity at this point, I said in the beginning of the video that at this point, we have not released it. Our velocity is 0. We just want to release it. So it's 0 meter per second. Now, when we release it, it starts increasing. Once we get to the main point, our velocity becomes maximum at that point, and it starts reducing again till we reaches this negative x, where our velocity is 0 back. Then it continues like that. It continues like that. It continues like that. It continues like that. Now, if we are not talking about the potential energy, remember potential energy is half kx squared, and our x is something. So wherever at this point, our potential energy is maximum because x is maximum. It is a here. So our potential energy is maximum here, which is equals to half k a squared like that. Because our x will turn to a, so it will become half k a squared at this point, which is our total energy. Now velocity is 0, and remember that our kinetic energy is half mv squared. Since it is half mv squared for kinetic energy, then v is 0, everything becomes 0. Then our kinetic energy here is 0. Then the total energy is equals to potential energy, because if you add potential energy and kinetic energy together, our total energy becomes kinetic energy, and that is true from this formula that we can see, because that is the formula for our total energy. And at this main point, we can see that our velocity is maximum, so therefore our kinetic energy also is maximum at that point, because it depends on velocity. And our potential energy is half kx squared, and x is 0, so everything becomes 0. So at this main point, our potential energy also is 0, and total energy is equals to our kinetic energy, since we are adding both kinetic energy and potential energy together. At this end point also, our kinetic energy, since it depends on velocity, will be 0, and our potential energy, since it depends on x, will be maximum also. And at this point, the total energy will be equals to our potential energy at that point also. Now, at any point in between the system here or here, our total energy will become potential energy plus kinetic energy. Note that our total energy become potential energy plus critical energy at any point in this space. And mind you, x is from this main point to any point, not from this maximum point to any point. It's from this main point. That is for our total energy. And mind you, note all these formulas that we have derived very well. In the next video, we'll be using this formula, each of them. If you find this video helpful, please click on the like button, subscribe, and please share to your friends that will be needing it. Thank you very much, and stay tuned.